Okay. So this is my plan for today. But let me pause here and see if anyone wants to ask any questions following the recap. No questions?
Where is Spartan situated in this?
Great. So Spartan is a sum check based polynomial IOP targeted, well, originally described for proving R1CS, but it's actually much more general than just R1CS. Um, and so, yeah, at its core is a PIOP. The original Spartan paper combined the PIOP with the Hyrax commitment scheme, but you can combine it with any multilinear commitment scheme. Yeah, so Spartan is based on the sum check protocol. A little more specifically, it's in like the subcategory that I call based on multi-prover interactive proofs, which tend to have somewhat shorter proofs than something like the GKR protocol. GKR is kind of polylogarithmic size proofs. Spartan is logarithmic size, plus whatever comes from the polynomial commitment scheme. Yeah, is that enough detail?
Yep.
And another question is I think the Lasso paper, they talk about a polynomial commitment scheme called SONA, which I think is like a
Mm-hmm.
mix of Hyrax and Nova.
Mm-hmm.
How would that work?
Yeah, so I would just I would call that so Hyrax is in, of course, the second category of polynomial commitments. Nova is more of a proof system, and it's based on folding, so kind of doesn't quite fit into this framework I described of a polynomial IOP plus a polynomial commitment. And so what's going on there is Hyrax has some really nice properties for the prover, but the verifier costs are somewhat big. So the proof like the size of evaluation proofs, when the verifier says, "Hey, I have to evaluate the committed polynomial at this point. Tell me the evaluation and prove that what you say, what you responded with is correct." So the evaluation proofs are annoyingly big. They're square root n size if n is like the number of coefficients in the committed polynomial, and the verifier time is also square root n, like group operations or something. So what SONA says is rather than declare the Hyrax evaluation proofs to be like the final evaluation proof, instead compose with Nova. So that is use Nova to prove, the prover knows like a valid Hyrax evaluation proof. And in that way, Nova has, depending on, well, let's just get the asymptotic cost of Nova kind of depends on what you call constant. So let me not let's just say about 10 kilobyte size proofs, roughly. Nova itself, you sort of have some flexibility in what polynomial commitment scheme you use within it. But yeah, so in this way, you kind of bash the proof size and verifier time of Hyrax down from root n to something much smaller. So 10 kilobyte size proofs and like a faster verifier than Hyrax had. So SONA is sort of an example of SNARK composition, where you might have a SNARK where you really like its prover efficiency, but you're not super happy with its verifier efficiency. So instead, what you do is you use like a fast verifier SNARK to prove the proof of the fast prover SNARK. And as long as the verifier of the fast prover SNARK is like simpler than just solving the statement from scratch, then the recursive proving shouldn't be a bottleneck. And so SONA is an example of that. Now SONA hasn't been fully implemented yet, just FYI. But anyway, in principle, it sort of is one of these best of all worlds situation where you get like the the nice prover properties of hierarchs, but you don't pay the verification costs, which are sort of the main downside of hierarchs, because you compose with a smaller verifier called SNARK. Yeah, was that enough detail?
Yeah, that is good.
Great. Yeah, good questions. Other questions? I think the questions are.
Quick,
Go ahead.
just a quick question though. When you say that, like when we talked about Spartan, Hyperplonk, and Jolt and Lasso, we said they are like multi-interactive proofs. But here, what we mean by saying multi-provers, like, are there more than one provers there?
Yeah. So no, there isn't. So what's going on is these protocols were often developed before the notion of a polynomial IOP was formalized. And so these protocols, these polynomial IOPs were originally presented not as polynomial IOPs. So like Spartan and its predecessor called Clover were originally presented basically as multi-prover interactive proofs. Spartan knew the end goal of Spartan was a SNARK. So like it basically knew that it was giving a polynomial IOP and combining it with a polynomial commitment scheme to get a SNARK, but without using the word polynomial IOP. Now, what's going on is, so like a multi-prover interactive proof, like on its own, is like not particularly useful in the real world, because in the real world, there's only going to be one prover typically. But effectively, what's happening is the second prover in the multi-prover interactive proof is really just functioning as a polynomial commitment scheme. So you can kind of, once you have a polynomial commitment scheme, you can just get rid of the second proof. And that's why you get a single prover SNARK. Now, the reason the book sort of distinguishes between MIPS and interactive proofs is roughly once you have a commitment scheme or a second prover, depending on how you want to view the protocol, like Spartan, you have the option of sort of using the sum check protocol like just once or maybe twice to check like an entire circuit like all at once. Okay, but if you did not have a second prover or a polynomial commitment scheme, you wouldn't have that option. And if I gave you a circuit and I said like, prove to me you evaluated the circuit correctly, as far as we know, like you really would have to like apply the sum check protocol like many times, like once per layer of the circuit or something like that. And so that's what these two categories are referring to, really, is like the multi-prover interactive proof-based PIOPs. They kind of like check the whole computation, the whole circuit, like all at once, with a single sum check. And of course, almost all of you probably have any idea what I mean by a single sum check, but don't worry about it. Whereas a single prover interactive proof like the zk-SNARK protocol, as far as we know, really has no choice but to check, the computation, like kind of one piece at a time, one layer of the circuit at a time. So that's really the distinction here. And you see this in the performance profiles of the SNARKs that come out of this, where in something like Spartan, the prover commits to more data than in a SNARK that comes out of the zk-SNARK protocol. But the Spartan proofs can be shorter. So there's trade-offs everywhere. It's like if you don't bring in the the second prover in the multi-prover interactive proof, you get the benefit of having less data ultimately be committed, but you sort of pay a price where the proofs potentially get larger. Okay, so hopefully that gives some color. It's a little bit of a hard question to answer when we haven't actually seen any details of these protocols yet.
Yeah, sure. Thanks.
More questions?
So I might have another question. you mentioned that like interactive proofs like zk-SNARK, they proof like multiple times. It's not a single subject. So does it mean that those are like more, it might sound counterintuitive, but does it mean that they are more suited for parallel proofing, or
No,
because they're multiple
so
times?
you know, I mean, it's a great question. So like, and to give a little more context for the whole group, small depth circuits correspond to highly parallelizable computation, basically because you can evaluate each layer of the circuit as you go from inputs to outputs, like in parallel. And so like the total like parallel time is like number of layers. You know, it's like you can in parallel evaluate like every gate, you know, just adjacent to the inputs, and then once you're done in parallel, you can evaluate every gate, you know, adjacent to those gates, and so forth. So it is true that the GKR protocol will lead to very, very big proofs unless the computation being proven is kind of is highly parallelizable. Okay, but you have this funny situation in SNARK design where our circuits are allowed to have what's called untrusted advice inputs. Another way, like the theoretical way of saying that is people call it non-deterministic inputs, but really it's like untrusted advice. And so once you're the reason you're allowed to have untrusted advice in the circuits that SNARKs prove is because we have commitment schemes. And so, you know, if you had to send explicitly all the untrusted advice to the verifier, that would be a problem. And in general, there'd be a ton of untrusted advice and the proof would get really large. But because the prover ultimately can just commit to all the untrusted advice, it's actually okay to have a lot of it. You do pay some price in terms of prover time to commit to all those untrusted advice inputs, but you know, you're going to commit to a lot of stuff anyway. And so maybe it's okay. And so once you know, recognize that our circuits can take a lot of untrusted advice, actually small depth circuits are universal, right? In the sense that you can literally take any computer program and turn it into a small depth circuit, where the small depth circuit takes a whole lot of untrusted advice as input. The untrusted advice literally specifies like everything the computer program did at every single step of the computation. You know, if the program ran for like trillions of cycles, the untrusted advice now has, you know, many terabytes of data in it or something. But once you have all that untrusted advice there, now the circuit can, in a highly parallel way, just check that all the untrusted advice is correct. Okay, and so to summarize, I would say GKR-based SNARKs are not really more or less parallelizable than other SNARKs. Like the small depth circuits correspond to highly parallel computation, but once you recognize that the prover, you know, is able to commit to all, you know, large amounts of untrusted advice, the circuit that the prover is going to prove it executed correctly actually can automatically always be small depth, and hence captures a parallel computation. So yeah, like it does turn out like you know, some check based SNARKs are like, in my view, they are the most parallelizable. That's probably a controversial view and needs to be fleshed out more with systems building and stuff. But it's not really coming in because the circuits are small depth or anything. It's coming in because some check-based SNARKs like the GKR protocol avoid operations that are hard to parallelize, like FFTs and things like that, depending on what polynomial commitment scheme you combine them with. So, okay, so that was probably a very hard answer to follow, but hopefully it was not helpful. All right. Okay, so I will proceed. Feel free to jump in with more questions as I go. But I think the questions are great, and I hopefully they're you know, I expect that they're useful not just for those who actually spoke up and asked them. Okay, so let's start with an example
Hello,
polynomial
Professor.
IoT. Oh, go ahead.
Yes. So this is in reference to something that was told last day, and this is like I'm more looking for an intuitive direction in the sense that a polynomial commitment scheme is enabling the prover from not having to send all the coefficients of the proof polynomial. That's what was told last week, and I'm just continuing from that. So one way to intuitively do it would be that giving enough evaluations of the proof polynomial, right? That's what we do, but so what are intuitively the other unique ways of ensuring soundness without having to send all the coefficients of the proof polynomial? This is one,
Yeah, well,
and the
what I would say is, okay, so so you mentioned sending like evaluations. So okay, there are multiple ways one could write down like describe a polynomial, and one is to give its coefficients. If it's a univariate polynomial, when people talk about coefficients, they normally mean in what's called the standard monomial basis. So they mean like you write the polynomial p as sum from 0 to the degree of ci times x to the I, and these are the coefficients. Okay. But you could also specify a polynomial with its evaluations over a large enough set. Now in the univariate case, the size of the set would, so another way to specify it would be to write it as so I call this this would be coefficients in the standard monomial basis. But there are other bases you could send the coefficients in. So one is I call it the Lagrange basis, and that's equivalent to sending evaluations. So that would be sending like p of j for all j in and what's called an interpolating set. Okay, and but the size of the interpolating set for a degree d polynomial has to have size at least d plus 1, which means like the description of this description is just as big as this description. They're the same size. They're just different ways of describing the same object. Okay, and so for the prover to actually send the polynomial to the verifier, it's like kind of just as expensive whether you send the coefficients or evaluations. If you try to have the prover send fewer than d plus 1 evaluations, but it's it's sending a degree d polynomial, well, it actually hasn't fully specified the polynomial, and it could kind of later on like change the polynomial it means once it does finally fully specify the polynomial. And so that's exactly what a commitment scheme is trying to avoid. So with a commitment scheme, I can give you, a commitment scheme is what I would call like cryptographically compressing. So the commitment itself will actually be vastly smaller than either of the descriptions above that fully describe the polynomial. So like information theoretically speaking, the commitment does not have enough data to describe the whole polynomial, but what you do is you show like, unless the prover can break some crypto system or something, there's only one polynomial it can possibly know of that opens up the commitment successfully. So it's like, while there are many different degree D polynomials that can open up the commitment, for the prover to know more than one of them, it would have to, implicitly break a crypto system or something. And so I can give a little example of what a naive polynomial commitment scheme would look like. This is very, very naive, but you could take like all evaluations, maybe over the interpolating set or something of the polynomial, so P1, P2 up to P, D plus 1 or something, if that's your interpolating set. The prover could write them all down in its head, but not send them to the verifier. And the commitment to them could just be what's called a Merkle hash of those evaluations. And so the details of that aren't really important right now. But that sort of compresses, these D plus 1 evaluations of the polynomial down to just like a 256-bit hash value. Okay, and just those 256 bits represent the commitment to these, D+1 values. And again, you give me any 256-bit string, and there's actually a huge number of of D+1 values that would hash to the same string. But unless the prover is able to find collisions in the collision-resistant hash function you use to build the Merkle tree, it's only going to be able to know of a single opening. And so it's almost as if the prover literally sent all D+1 coefficients, even though it only sent 256 bits, not D+1. Did that make enough sense to give you intuition?
Yes, sir. But thanks a lot for the explanation. My question was that this is something that we are doing just to, on an application level, to make it to manifest this particular line. I was asking that information theoretically, is there any other way of doing this rather than having to give out D+1 evaluations by some crypto help?
Yeah, I don't think so. I mean, again, like you can, there's sort of an infinite number of ways to describe, like one could describe like a degree D polynomial, but all of those ways, have the same length. They all, ultimately write down like D+1 numbers some way or another. And yeah, so sort of without cryptography, without a commitment scheme, there's no way to convey the polynomial to the verifier with sending fewer than D+1 numbers. And then, the whole study of polynomial commitment schemes is like, how can you bring in cryptography to avoid the prover sending those D+1 numbers, but make it almost as if the prover sent them anyway? Does that,
Yes,
maybe
sir.
I'm saying this misunderstanding and
No,
sort
no,
of
that's okay.
not,
What I
yeah.
was trying to, so I had one, maybe this question doesn't have any answer, but I just have to ask this. So why is it that the ZK community has never looked into, say, black box PIT testing as one of the ways of just committing to uniquely to a particular polynomial? I could have just committed to those particular evaluation points and you were done.
Yeah. So no, this is a great question. So the key thing is if the prover knows when it's committing, which points the verifier will like check the polynomial at, then it can cheat. Then you'll lose security because it'll sort of wind up having the prover say like, okay, so let's say you have a polynomial p that's garbage, okay, and a polynomial q that's like correct, right? And if the prover knows, like before it ever commits to anything or sends anything, that the verifiers, like polynomial identity testing, the way it would work is it would like evaluate p and q at the same point r, and like try to figure out, so it'll that if the prover, yeah, it'll inspect like any polynomial the prover sends or commits to or whatever just at the point r, and try to ascertain like does the evaluation just at r like look correct. And if the prover knows in advance what r will be before it ever commits to anything, it'll just pick something that's garbage everywhere, like except at r. Like it'll just so it'll just make things look good at r even though they're garbage everywhere else, and it'll still pass the verifier's checks. So effectively what SNARKs do is polynomial identity testing, but they can only determine what r is, what the point you do the identity testing at after commitment.
So is it just safe to conclude that we don't know of any other ways of information theoretically uniquely ensuring soundness without having to give out D+1 points?
Yeah, I'd say that's right. So yeah, if you want to, forget commitment scheme, just talk about polynomial IOPs. I'd say that's correct. And there might even be formal lower bounds known in some variants of the polynomial IOP model that basically says, the prover cannot possibly send less than D+1 numbers, where D is like some measure of the size of the statement being proven. Like it should just be, it should just be impossible, like basically, I don't know, there should be some kind of incompressibility result that says like, if the prover is claiming to know a witness of size D or D+1 or something, then there's no way to get around the prover, like sending D+1 numbers to the verifier until you bring in a commitment scheme, something like that. So, I'm sure there are also open questions, it depends how you formalize, what the prover is allowed to do or send or whatever. But yeah, conceptually, intuitively, there's no way that you just shouldn't be able to go below the size of the witness the prover is claiming to know.
Thank you, sir. Thanks a lot.
Yeah, that's a great question.
I
And
have a
I'm just
small
watching-
request.
Yeah, go ahead.
Can you please emphasize on what defines the constraint system for each proof system? Because I see that as very important for developers, like to have a grasp of what's going on behind the proof system. Because like a circuit in R1CS is not is not efficient in a clunkish system. So it would be really useful to know what's going on behind in every proof system when it comes to constraints.
Yeah, sounds great. Okay, I'll do that quickly now, and then of course, as we go through how these proof systems work, we'll see it in much more detail. Okay, so Marlin was described for R1CS, but in fact, it's significantly more general. So I have like a note that introduces a generalization of R1CS called CCS. That actually also generalizes Planckish and Air. So both Spartan and Marlin actually apply to CCS. Planck applies to something called Planckish constraint systems, which is technically incomparable to R1CS, but is like a special case of CCS. SNARKs apply to something called Air, which is, in my view, basically a special case of Planckish where the constraints have a lot of repeated structure in them. But I won't go into more detail than that right now. Growth 16 is pretty specific to R1CS. Like it really can't go beyond R1CS. Well, okay, it definitely can't go beyond degree 2 constraints. It can go beyond rank 1, but the verifier cost would go up if the rank goes up. And if you don't know what rank 1 constraints are, don't worry about it. It's kind of like the number of multiplications in each constraint, but yeah, don't worry about it. zk-SNARK roughly captures arithmetic circuits of low depth. Although again, like once you allow not untrusted advice inputs, low depth is sort of, universal, captures anything. Lasso is what's called a lookup argument. And one way of viewing lookups is, this is my personal view. It's this sort of differs from how most people view them. Lookups involve when the prover evaluates the same simple function f on many different inputs. So x1 to xn, where n is like very large. I won't say much more than that right now. Hyperplanck is targeted at Planckish, and Jolt is what's called a zk-VM. So that means the prover is proving a statement of the form, I ran a computer program specified for this particular CPU architecture on a witness. So it's very, zk-VMs are specific to proving you ran computer programs specified for a certain simple CPU architecture. So with the exception of sort of lookup arguments, which are specific to lookups, and zk-VMs, which are specific to proving you ran computer programs for specific CPU architectures, like everything else is using circuits or R1CS or Planckish or Air or CCS, which is some kind of effort to unify and generalize everything that people are using today. So and then when I talk about like Marlin and Spartan extending the CCS, the actual implementations that are available for use today are specific to R1CS, right? So like, in principle, protocols, directly generalized handle CCS, but that doesn't mean anyone's implemented the generalization yet. So that's a quick overview, and I'll certainly talk a lot more about this in the future.
Thank you for the explanation.
Yeah, great. No, it's a great question, and it is really important. People have there's differing opinions on like, should I think of Planckish constraints as more expressive than rank 1 constraints, but and I won't get into today my personal views on questions like that, but what is sort of undeniable is like right now the tooling is sort of annoyingly fractured. Right. So like, if you want to use a growth 16 backend, you have to go through R1CS. You can't go through Planckish constraints. But, like Halo 2 is popular tooling that lets the developer specify Planckish constraints. So, and then actually, I think if you want to generate the constraints in an automated manner via like an automatic front end or something, we don't actually have automated compilers that leverage the expressivity of Planckish. So what people would actually do is use an automated compiler like Circom that spits out R1CS. And so what that means, and then possibly transform the R1CS into Planckish. So what that means is if you want to leverage any extra expressivity in Planckish that's not available in R1CS, you really have no choice but to write your Planckish constraint system by hand today. And so knowledge of like what backends support what constraint systems is like super duper important if you're trying to decide what tooling to actually implement, your proof system in today. And I really do hope that as, in the near future, this landscape gets less fractured. The introduction of CCS was an attempt at this. Since CCS kind of generalizes everything people use today, all the constraint systems people use today, if people sort of, converge around SNARKs that all support CCS, then you could have, just one backend that proves all the constraint systems people have ever designed before. And then sort of another effort to unify the fractured landscape is to just focus on zk-VMs. And then you sort of have a double win where, for one, no constraints are ever exposed to developers. Like developers would just write like high-level computer programs that automatically get compiled down to assembly code for the VM architecture you choose. And on top of that, like under the hood, a zk-VM like Jolt doesn't use any fancy constraint systems. It's purely lookups and R1CS, at least today. It might change in the future. So that's sort of a double win of potentially this fractured state of different projects, different tools use different kinds of constraint systems, might get less fractured as we kind of figure out or converge on the right way to do things.
Actually, after your explanation, like you described what are the constraints for growth 16 for other proof systems, and actually that became quite abstract to me because the building blocks are not common in those. For example, linear PCP for growth 16 and other systems, they have polynomial IOP. So what connects the constraint system to the building block? Like, is it the commitment scheme? Is it the polynomial IOP or anything of that sort?
Yeah, it's the polynomial IOP. The commitment scheme, you can just use any commitment scheme typically. I'd say the one exception might be growth 16, where the restriction to degree 2 constraints is really coming in because of the way it uses pairing-based cryptography. Pairings let you sort of check one multiplication with so it lets very quickly a pairing lets you take 3 group elements, G to the A, G to the B, G to the C in a multiplicative group, And, without knowing what A, B, and C are, a pairing will let you check whether A times B equals C. Okay, and so it lets you check one multiplication, like, of sort of hidden values. And that's why Gross 16 is like really fundamentally limited to degree 2 constraints. Degree 2 captures like one multiplication, and Planck and Marlin, they also use KZG. They use similar cryptography. They use KZG commitments, which uses pairings, but they're not so limited to degree 2 constraints because so they move beyond degree 2. And in my view, I'd say the way they're doing this is because they use interaction in the polynomial IOP to reduce checking higher degree constraints down to degree 2 constraints. And what's really very specifically, these degree 2 constraints are polynomial evaluations, right? So what's happening here is if I give you polynomial Q and the coefficients are, Ci times x to the I, say, then if I ask you for Q of R, that's actually an inner product between two vectors. Let me call them C arrow and capital R arrow, where C arrow is just the coefficients of the polynomial and R arrow is the powers of R. Right. So, this sum here, if I plug in R for X is just the inner product of this vector and this vector. Okay. And so inner products, this is a degree 2 thing right here. It's degree, it's degree 2 in like C and R. And so the polynomial IOP sort of, reduces the general constraints down to the verifier just needing to evaluate a committed polynomial at a single point. And that's like a degree 2 thing. And then it uses KZG commitments involve pairings to handle checking that degree 2 thing. So in summary, in my view, the relationship between like what constraint system is supported by what proof system is mainly coming from the polynomial IOP, and Gross 16 is just a little funny because it sort of it doesn't have such a clean line between the polynomial IOP, really linear PCP, and the polynomial commitment scheme, really the cryptography that turns the linear PCP into a SNARK. So hopefully that's enough color that you get some answer to your question.
Thank you for the valuable information. It's amazing. Thank you.
Yeah, sure. Yeah, great questions. Okay. All right, so we're like an hour in, and I haven't gotten to the new content, but normally that's actually a good thing. So hopefully you've all enjoyed the questions and answers. I do want to cover some new content today, so let me just dive in. I think I can get through most of this I really don't want to go past 90 minutes. Last time we did like 2.5 hours, which is just not sustainable. So I'll try to get this all done in the next 35 minutes or so. Okay, so let's do an example polynomial IOP. It's not one you would ever want to use, but actually it's good to see this example. I think I might actually put this into the book. Let's talk about, for simplicity, a circuit that only has multiplication gates. And actually, these circuits actually are really important for what's called grand products. But let's not dive into what that means. But grand products come up a lot where you're just producting together like many committed values. So we have a circuit of multiplication gates. We have some inputs, let's say x1, x2, up to what it looks like there's going to be up to x8 here. Okay. And the prover wants to, so I don't, let's say you could either have these 8 values be committed, or maybe the verifier even knows them. And the prover wants to claim that their product is some other value. So let me just give all gates in this circuit like a value. So like this, I'm going to call this one x9, which, you know, if the prover's honest, is the product of x1 and x2. Here we have x10, x11, x12. You know, if the prover's honest, like x12 would be x7 times x8, right? x13, x14, x15. Great. Okay. And so the prover's claim is that like, you know, some value, say w equals, you know, product from I equals 1 to 8 of xi. Okay. And so here's one way the prover can prove it. So it will just so let G be a univariate polynomial. Such of degree, I guess, would be 14, such that G of I equals xi for I equals 1 to 15, right? So that this is called, you don't need to know this yet, but this is called the low degree extension, the univariate low degree extension of like the gate values. Later in the book, I'll call it like a circuit transcript. It really doesn't matter. So like G is like a polynomial that sort of assigns a value to every gate in the whole circuit. Okay. And, you know, so yeah, so this would be like what the prover in the polynomial IOP sends like as its first message in the protocol is the like, you know, this degree 14 polynomial. And you can see this polynomial has size equal to the size of the circuit. Like there's one, you know, there's one degree, one coefficient for every gate in the circuit or whatever. And that's what I mean by in these polynomial IOPs, the prover sends these polynomials and the polynomials are really big. And so you don't literally want the prover to send those polynomials to the verifier. Instead, it's just going to commit to them. Okay, now what does it mean for you know, G to actually assign the appropriate value to every gate in the circuit? Well, this would involve checking the following constraints. So I guess the main one would be that for every multiplication gate, so what would that be? 9 up to 15? You would want that like G of, so let me call that J. So for every one of these multiplication gates, you would want that G of J is the product of the first in neighbor of J times the second in neighbor of J. Yeah, so this is saying like, you know, that G of 9 is the product of the values that G assigns to the first and second inputs. You know, and similarly, like G of 13 should be G of 9 times G of 10, because G of 9 is ostensibly the value of this, you know, the first input to gate 13, and G of 10 is the value of the second input to gate 13. Okay, so yeah, so these constraints sort of confirm that the value assigned to every gate is the correct value. That, you know, it respects the operation of the gate. That the gate, you know, that each gate in the circuit is supposed to, you know, compute the product of its two in neighbor gates. Okay, and then there's just like that's like the bulk of the constraints, I would say, and then there's just like making sure that the inputs and outputs are correct. So you would have like for inputs, you know, I equals 1 up to 8. You want that like G of I equals xi, you know, so that G assigns the right values to the inputs. And you want that, you know, for the output gate, which is 15. So G of I equals the claimed output, which is I just called that W before. Okay, and let me just ignore these input and, you know, these are called IO consistency constraints. Let me just ignore them, since again I think the, you know, like the correct operation of gates constraints is really sort of the key. And so yeah, another way of writing these constraints is that, you know, for J equals 9 up to 15, you want that G of J minus G of in1 of J times G of in2 of J is 0. You know, Okay, so that's, let's say these are the constraints we want the prover to prove. So, it's set G, but the verifier ultimately, we don't want the verifier to have to read all of G. The verifier is ultimately going to just want to evaluate G at like a single point, or, maybe 3 points or something. And so there's the question, like, how can the verifier check all of these constraints, like one per gate in the circuit, while evaluating G at only like 1 or 2 or 3 points? Okay. And the way that most univariate polynomial-based SNARKs work, which I called constant round polynomial IOPs before, is the following. So they do something called quotienting, or like I don't know, people call this like a vanishing argument or something, which is the following. So let me call this set of, the labels we assign to the gate to the circuit, let me call it S. So this is there's a set S of in this case it'd be 9 up to 15, but in general it's just whatever we labeled the gates with. And so you would have that for all J in S, G of J minus G of in 1J times G of in 2J equals 0, if and only if the following is true. Okay, and by the way, we're gonna need G, okay, so it turns out that G composed within 1, this turns out to be a polynomial of degree at most n squared. Okay, and what's going on is, like, in 1, just through we only care about how in 1 behaves over so n here is circuit size. It's like we only what we want in 1 to do is like map each gate. So in 1 of J maps gate J to its first in neighbor. So back to the example, in 1 of J would map like in 1 of 9 would be 1, because x1 is the first in neighbor of gate 9, and in 2 of 9 would spit out 2, because the second in neighbor of gate 9 is 2. And similarly, like in 1 of 15 would be 13, and in 2 of 15 would be 14. So just through interpolation, we can ensure that in 1 and in 2 are degree n polynomials, because we only care about their values at n points. And G is itself a degree n polynomial, and so their composition has degree n squared, right? And so it turns like so if I give you so what's going on here is like let's say Q of J be G of J minus G of in 1 of J times G of in 2 of J. I shouldn't use, so H of J, they call that H of J. So H is a degree n squared polynomial. And there's just like a fact that H of J equals 0 for all J in S, if and only if, well, that's what we want to check. And sorry, so this if and only if should be down here. Sorry. So H of J equals 0 for all J in S, if and only if H of J is divisible by what's called the vanishing polynomial of S. By the way, if you don't follow everything I'm saying here, like, it's really, the details are not that important. I'm just trying to give a sense of how these SNARKs work, just so that when I talk about what the prover has to do to compute the SNARK proof, you have some idea of like what's going on. If I literally told you almost nothing about what the prover is doing, it'd be very abstract. I'd start talking about the cost of group operations and hashes and blah 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 blah, and then you just have no idea why the prover would be doing these things. So what is the vanishing polynomial of S? It's just the lowest degree polynomial that evaluates to 0 at all inputs in S. So that is so this vanishing polynomial, people will often denote it like bold Z sub S. This is the product over all K and S of X minus K. Okay, so that is where this polynomial is making sure that if you feed into it anything in S, it spits out 0. So it kills everything in S, and doesn't kill anything else. Okay, and so you know, if h of j is divisible by the vanishing polynomial for s, then clearly h of j equals 0 for all j and s. You know, just so if we can write h of j as something times the vanishing polynomial, then you know, then this by definition, you know, evaluates to 0 for all j and s. Okay, but the reverse implication is also true, which is if h of j equals 0 for all j and s, then there is some polynomial q of degree at most n squared or something like that, maybe n squared minus size of s, which is something like n. You know, that you can stick in here. Yeah, this is called the quotient polynomial when you divide h by the vanishing polynomial. Okay, so this is like the key fact that underlies like all univariate polynomial-based polynomial IOPs, including Marlin and Planck and Starks and even Gross 16. Okay, and so this is called like quotienting. It's so checking that this is called like a constraint polynomial, you know, checking that the constraints all evaluate to 0, you know, and there's one input j that you care about per constraint or whatever, is equivalent to making sure that the polynomial, the constraint polynomial evaluates to is divisible by the vanishing polynomial for the set S indexing the constraints. Okay, which means this is how the polynomial IOP works, to summarize. So let me just summarize it. So the prover first sends G. Okay, now again, if the prover's honest, then G satisfies all of these constraints in this box here, one for each, you know, like gate J of the circuit. That is equivalent to this polynomial H, which has degree like n squared, evaluating to 0 for all j in the set S. For my example circuit, this was like 9 up to 15 or something. That in turn is equivalent to H being divisible by this vanishing polynomial, you know, which has degree n or whatever, whatever the size of S is. Again, the size of S is like one element of S per gate in the circuit. I'm using n to denote like the number of gates in the circuit. So the prover sends G, then it sends Q, this quotient polynomial, and then the verifier wants to check that that H, which is, remember, H is G, H was G of X minus G composed with in1 of X times G composed with in2 of X. And so the verifier wants to check that H of X is Q of X times the vanishing polynomial for the relevant set at X. And it does this by picking a random input R. These polynomials turn out to be defined over what's called a finite field, but don't worry about that right now. So it picks R at random and checks that just that this equality holds at a random point. So H of R equals Q of R times the vanishing polynomial at R. And what's happening is, you know, if H does not actually equal Q times the vanishing polynomial, then it turns out that if you evaluate them both at a random point, this equality is very unlikely to hold. So, you know, this is how like all polynomial IOPs tend to work, is you sort of identify like some equality of polynomials which holds like if and only if the prover is being honest, and then the verifier winds up checking that the equality holds at a random point. And, you know, the fact that any two low degree polynomials that are not the same can agree at only a very small number of points means that sort of this check, you know, unless the prover gets really lucky in the choice of R, this check is more or less equivalent to the checking just at a single point. Okay, and that's how the polynomial IOP works. And so for this reason, you know, to evaluate H of R, remember H of R is just G of R times G of N1 of R times G of N2 of R. So the verifier only needs to evaluate G at the points R in 1 of R and in 2 of R. So that's how you get the situation that even though the the prover like sent all of G to the verifier in the PIOP, but ultimately the verifier didn't need to know all of G. It only needed to know the evaluations in 1 of R, in 2 of R, and in R. So that's three evaluations of G.
So is it,
Go ahead.
Professor, can I ask a question? Yeah. Is it safe to conclude that the proof polynomial is itself the circuit that you drew, such that this line of work had to first degree extend in order to ensure correctness of every gate?
Yes, that's exactly it. So this G, basically the prover just evaluated the circuit gate by gate, thereby getting a value for each gate. And then this G is just like what's called the low degree extension polynomial of that function that assigns a value to each gate. Yeah. So,
Right, so the proof polynomial is itself the circuit, right? That's the way the mental model should be.
yeah, well, it's the circuit and then some extra stuff because the prover also sent Q. Okay, and actually this Q is in large part why the sum check protocol is so nice because in the sum check protocol the prover would never send this Q, or not only would it not send this Q, but it would never compute the Q either. But the univariate polynomial based SNARKs, they all somehow this Q comes in some way or another, this quotient. So this is called the quotient polynomial. That's why I said these, constant RAM polynomial IOPs that use univariate polynomials, they're all based on quotienting. So yeah, so it's like these SNARKs, they basically always have the prover send the circuit itself, really like the low degree extension polynomial of the circuit. The only SNARKs that avoid that are partially avoid that are based on the GKR protocol, but we don't have to get into that. And the univariate ones have the prover send or commit to extra data as well, such as the quotient polynomial. Some of them avoid explicitly committing to the quotient polynomial, but there's still some costs that come in because of the quotient polynomial. So it's the circuit is part of the proof, but there's other parts of the proof as well. Does that make sense?
Yes, sir.
Excuse me, please. I wanted to ask one too. What is the length, the degree of the vanishing polynomial?
Yeah. So
What is-
yeah, good. So its degree and it's linear in the number of constraints that the number of points that vanishing has to be checked at. So in this case, it would be linear in the number of gates in the circuit. Degree n is number of gates in the circuit. Yeah, and so what's happening is so as I've described it, G and Q would be committed by the prover, but this vanishing polynomial, the verifier would deal with. So the verifier in these SNARKs would wind up computing the vanishing polynomial at R on its own. And so typically, what will happen is we'll choose S so that the vanishing polynomial is sparse or just quickly evaluatable. So often what will happen is we'll choose S so that the vanishing polynomial for S is like R to the n minus 1. And that's why you'll see a lot of these univariate polynomial based SNARKs choose S to be the nth root to unity in some finite field. And that means, because we don't want the verifier to take time n. We want it to take time at most like log n or something. And so, if the vanishing polynomial is just an arbitrary degree n thing, it might take time n for the verifier to evaluate it at R. But if it's really sparse, if it has like 2 coefficients, if it's R to the n minus 1, it can compute that in like logarithmic time. Does that make sense?
Am I correct that it means that the point R, random one, at which we check this divisibility, should never be a root of unity? Or
That is right. Yeah, if it were a root of unity, then is it? So, okay, one thing I say, if you choose R at random from the whole field, the field should be big enough anyway that you're very unlikely to pick a root of unity. So you might, I have to think whether like the check is just always going to pass if R is a root of unity. Even if there's not divisibility, I think it would. Yeah, I think it would. So yeah, I mean, I think you'd improve the soundness error slightly if you pick R from the whole field, other than the roots of unity, other than S. But the fields we work over are typically big enough that if you just pick R at random from the whole field, it's very unlikely to be a root of unity. So who cares? But yeah, I think you're right. I think you would, this check is trivially passed if R is a root of unity. Yeah.
Very interesting. Thank you.
Is what you explained here why they say Planckish constraints are non-zero entries regarding the multiplicative nature of constant round polynomial IOP?
Non-zero entries. You definitely run into some issues with quotienting when, like, you can't divide by zero, right? So that's a nuisance. Like, this quotient, you can express it as, the quotient Q is h of R over the vanishing polynomial at R. And so you have a big problem if this is zero because you can't divide by zero. Now, I think that issue mainly comes up if you're trying to avoid the prover literally committing to the Q polynomial, which some SNARKs try to avoid that. Yeah, so I think like this Q always exists. Like this division makes sense, as polynomials. This division makes sense as polynomials, no matter what. But if you don't literally have the prover send Q, there are some SNARKs that will implicitly define Q, to be like, rather than having the prover send Q or commit to Q, they'll just like implicitly define Q as this division. And then you run into a big problem. Like, so they'll define Q of R in this way, but like this definition, like, just doesn't work. Just doesn't make sense. If the denominator is zero, if ZS of R equals zero. So that's probably what's going on in, so certainly SNARKs try to do this, like what they'll do is they'll try to make sure Q is of the appropriate degree without ever having the prover explicitly commit to Q by applying the Frey low degree test to this quotient. And then you run into a big problem because, you just can't figure out what the quotient's evaluation is if the denominator over here is zero. So I'm guessing that's what you ran into, but I'm not 100% sure.
Thank you.
Yeah, great. Okay, so so you get a sense of what's going on in these polynomial IOPs. Now, the reason you would not want to use this polynomial IOP is because G composed within one, G composed within two has quadratic degree. And so the Q polynomial, the quotient, has quadratic degree. That's too big. Yeah, so the whole sort of sophistication in Gross 16 and Planck and Marlin is all to avoid that quadratic degree blow up. Okay, but this still captures like the main stuff going on especially in these univariate based SNARKs. You see how the prover, the first polynomial it sends is just capturing like the gate values in the circuit. And then it might also, commit to or send extra polynomials as part of its proof that, the first committed polynomial satisfies all the relevant constraints. Okay. All right. Great. So now I have 10 minutes left to talk about SNARK costs. Let me. I think I can say something useful. I'm probably going to take another 20 minutes. But I think I can. Yeah. Anyway, I'll do my best. I don't want to talk about this next week. I'd like to just dive into chapter 2 next week. So I will take the time I need today. And hopefully this successfully gets recorded, and anybody who can't stay can just look at it at your leisure. Okay, so what happens? What do the SNARK provers do in these SNARKs? Okay, so obviously they commit to polynomials. Okay, but then they also, in what you just saw, the prover also had to compute a quotient polynomial Q. And if you use the sum check protocol in your polynomial IOP, you won't have to, the prover will never have to compute a quotient polynomial Q. So in that case, you know, for sum check, you know, the prover does, you know, a lot of field operations. That just means like adding and multiplying numbers together, you know, to compute various polynomials. They're not quotient polynomials, you know, not for the purpose of computing quotient polynomials. And then the final thing the prover does is the prover computes like evaluation proofs for the polynomial commitment scheme. You know, when the verifier says, hey, I have to evaluate like the committed polynomial or polynomials at, you know, 1 or 2 or 3 points, the prover has to compute proofs that, you know, it's returning the requested evaluation correctly. Okay, so let's talk about what happens in, first let's say the commitment schemes. Okay, so remember the commitment schemes, you know, fall into 3 classes, 3 categories, where the first category, the first 2 are based on groups, and the second is based only on hashing. Okay, and so I'll just tell you like roughly what happens in all polynomial commitment schemes in these 2 classes. So for the groups, like if the polynomial's coefficients are like you're committing to like Q of X equals sum over I Ci times X to the I. Okay, then the commitment to Q typically turns out to be what's called is like a multi-exponentiation. People will also call this multi-scalar multiplication. I'll tell you what that is in a second. Applied or over the coefficient vector. Okay, so what does this mean? So it's like I can describe this one of 2 ways. Let me describe it this way. Okay, so we want the commitment to Q to be, we want this to be one group element ideally, right? Like because Q itself has many coefficients, and we don't want to send all those coefficients to the verifier. We want to send just, you know, effectively compress all of those coefficients down to just like one value, one group element. Okay, let's say rather than trying to compress everything down to one group element, let's say first we just wanted to hide the coefficients from the verifier, but we were willing to send them all to the verifier. Okay, then what we could do is we could just take like a random group element G, you know, chosen at random, and what we could do is for each coefficient, we could just stick the coefficient in the exponent. So so we now, by sticking the n coefficients in the exponent of this one group element, we basically, you know, if discrete logs are hard to compute in this group, what that means is, I'm being very hand wavy here, like do not go and try to write a security proof that looks anything like what I'm saying. I'm just trying to be very intuitive here. So if discrete logs are hard to compute, what that means is given G to the Ci, it's hard to figure out what Ci is. So then intuitively, like Ci should be, you know, hidden from the verifier, because you know, given Ci in the exponent, the verifier can't pull Ci out of the exponent. That's what it means for discrete logs to be hard to compute. Okay, so that would hide the Ci's from the verifier intuitively, but it doesn't, there's still one group element per coefficient here, so that's no good. Okay, so instead, if we want to compress all of the Ci's down to a single group element, what we would do is let G1 to Gn be different group elements. And for something like bulletproofs, they would just be random group elements. For something like KZG, they would be what's called like powers of tau. This would be for KZG commitments, we discussed this briefly last week, the difference between bulletproofs and KZG. Details really don't matter today. And then, so what the commitment to the coefficients of Q would be is, this is what a multi-exponentiation is. So it'd be product, so this is group product of GI to the CI. Okay, so what's this doing? It's like, you know, we have taken these n values from before, one per coefficient. So we sort of hidden the coefficient and the exponent of some group elements. But we, you know, it's like we weren't happy with having n different group elements, one per coefficient. So we just munged them all together with one big group product to compress them all down to one group element. Okay, and roughly the idea is like, as long as the prover doesn't know any special information about the GIs, this is a binding commitment scheme, meaning like the only way to get a group elements of the form here is to know these CIs. And in particular, it's computationally, like you have to solve the discrete logarithm problem to find two different vectors, you know, like C arrow and C arrow prime, that both result in the same commitment here. So in this way, we sort of, you know, munge all n coefficients down into a single group element, but any polynomial time prover, you know, can only possibly know one coefficient vector that actually opens the one group element commitment. Okay, so this is called a multi-exponentiation. People will also call it multi-scalar multiplication. It's just a notational or terminology thing. MSM sort of refers to additive groups. Here, as we discussed last time, I like to use multiplicative groups in most contexts because I like to think about values hidden in the exponents. But if it were an additive group, this MSM would instead be sum rather than product of, you know, CI times GI. And people would call this a multi-scalar multiplication because here we have a scalar multiplication. You know, yeah, anyway, so it's just different terminology for the same thing. Okay, and so that's what happens in a group-based commitment like bulletproofs or KZG. In a hashing-based commitment, basically what we do is we take the vector of coefficients and commit to the vector just as we did up here, but in a very different way. So basically, very high-level sketch, the commitment here would take the coefficient vector. It would encode it with what's called an error correcting code. Don't worry if you don't know what that is, but so you would encode. And then the commitment would be a Merkle hash of the code word of the encoding, then Merkle hash the encoding. Okay, so in these commitment schemes, you know, if you use groups, the commitment tends to be an MSM. If you use hashing only, Frye, Binius, breakdown, whatever, the commitment involves an encoding step and then a hashing step. Great. And then outside of the commitments, basically everything the prover does is field work. So it's field work to compute a quotient polynomial, or, you know, some kind of composition polynomial, like of the form G composed within one, you know, of X from before. In the sum check protocol, the prover is doing, again, other field operations that don't look like quotients or compositions or whatever. And so this is everything the prover does, basically, is, you know, depending on your commitment scheme, it's group ops. So it's like MSMs, or, you know, encoding and hashing. Let me leave out encoding. Let's just not worry about it right now. And then field ops. Okay, like that, roughly, this is the key stuff the prover does. And similarly, the verifier also, like, this is roughly the key stuff the verifier does. The verifier might have to do pairings. I think the prover, it depends on most of the time the prover doesn't have to do many pairings. So, you know, if you care about the verifier, then V would also wind up doing, maybe not MSMs, it depends, but group ops operations, hashing, field ops, and maybe pairings if you use a pairing-based commitment scheme like KZG or something. Okay, these are all the key operations the provers and verifiers do. And now to understand, like, you know, performance of different SNARKs, we now have to have some understanding of, like, how expensive is it to do an MSM compared to field ops or hashing or something like that. Okay, let me pause here, see if there are any questions. But then the next and final thing I'm going to talk about, it will take me a little bit, is to convey the relative cost of these different operations, field ops, MSMs, hashing, and so forth. I think, you know, it's pretty, I think I can give a pretty clean overview of, like, you know, how much more expensive is an MSM than a field op, how much more expensive is hashing than MSMs or whatever. So yeah, anyway, does anyone want to ask any questions right now?
Is hashing binary or zk friendly in the case?
Yeah, so that's a great question. So the cost of this very much depends on what hash function you use. Depends on the hash function. And what hash function you use might depend on whether you want to use SNARK composition or recursion, maybe. And because, like, you know, a lot of people will want to do recursion, and to do recursion, they'll want to use what's called a SNARK friendly hash function. Basically, recursion means a prover is going to prove it knows a proof. And so if the SNARK verifier does a lot of hashing, proving you know a valid proof means proving you know, like proving you did a lot of hashing correctly, proving that you verified the proof. And so SNARK friendly basically means SNARK friendly hash is a hash function where it's efficient to prove you did the hash correctly. Now, I think we're moving to a world where there actually isn't so much difference between SNARK friendly hashes and standard hashes. So I think there'll always be, like, you can always tailor your hash functions to SNARKs to be friendlier to the SNARK than something like Blake or Ketchak or, you know, SHA or whatever. But at the same time, I think Ketchak and Blake and SHA and the hash functions people use, you know, when they don't worry about SNARKs, are vastly friendlier to SNARKs if you use sort of like the right kind of SNARK. So anyway, the answer to your question is the cost of hashing depends on the hash function you use, and what hash function you use depends on things like, are you going to do recursion? Which hash functions actually turn out to be friendly to SNARK recursion in the long run? You know, do you want to post the proof on chain? Because then certainly if your proof involves hashes, it would be ideal for your hash function to be like a precompile for the blockchain. Depends on all of these things. So mainly I want to flag the issues they depend on, rather than the decision depends on, rather than give you a, you know, a yes or no answer to your question or something.
So is it correct to say that recursive proof systems always involve hashing?
The only proof system that involves literally zero hashing is Growth 16, the only practical one. However, proof systems that use curve-based commitment schemes, only hashing for them only comes up in fiat Shamir. And fiat Shamir is generally pretty cheap, even when done recursively. So really what's going on is, if hashing is like, if proving you did hashes, in order for proving you did hashes correctly to be a major consideration or bottleneck, what that typically only comes up if you're using a hashing based polynomial commitment scheme, which today would mean Fry, but in the future is definitely going to mean something like Binius, or you know, there are, you know, other hashing based commitment schemes that are definitely going to become more popular in the future. Does that make sense? So the way
yes.
comes into SNARK verifiers is like from the commitment scheme or from fiat Shamir, but fiat Shamir generally not that many hashes typically. So the main concern is if you're using a hashing based commitment scheme like Fry or Binius, then the verifier does do a ton of hashes.
Which also related to recursion, right?
Yeah. So I'd say, yeah, I mean, like, you know, recursion mostly amounts to proving you verified a proof. And so if your SNARK verifier does a lot of hashes, then proving you verified a proof mostly amounts to proving you did a lot of hash evaluations correctly. Yeah. And so, yeah, but I do think it turns out that like we're going to wind up in short order with like much faster SNARKs or standard hash functions like SHA or Ketchak or whatever than we had previously. Because recent advances in some check-based polynomial IOPs and multilinear polynomial commitment schemes sort of unlock those much faster SNARKs. So that may well mean that we can do recursion on hashing with hashing-based commitment schemes much faster than we could previously, even when we're using, you know, like standard hash functions rather than things like Poseidon or, you know, whatever, you know, reinforced concrete or what have you.
Thank you.
Yeah.
And probably out of scope, but I know they're also for sparse multilinear polynomials, but where does like Spark and Surge fit into this landscape?
Yeah, so the Spark and Surge they're actually just generic like reductions. They're a way to build a sparse, like an efficient way to commit to sparse polynomials, given any standard polynomial commitment scheme. So, like if your standard polynomial commitment scheme is based on curves, then applying the Spark transformation to that will give you a sparse polynomial commitment scheme that's also based on curves. But if your standard polynomial commitment scheme is based on hashing, then applying Spark or Surge to that will give you a sparse polynomial commitment scheme that's also based on hashing. Does that answer the question?
Yes, thanks.
Great. Other questions?
Maybe, yeah, a question about the quotient method you mentioned.
Mhm.
Is there an easy argument or way to see that this h function doesn't become a degenerate polynomial or just a zero polynomial, so that it's really a polynomial of degree n squared?
That's an excellent question. Let me remind myself the definition. So I guess were it to be degenerate, I think it would still be okay, right? Because H, like the original like G satisfying the constraints the verifier wants to check is just equivalent to H vanishing over the relevant set S. And so the zero polynomial is an example of a polynomial that vanishes over the relevant set S. And so, you know, if H is the zero polynomial, that's okay. Like that still implies that the prover is being honest. So I think the answer to your question is no, but it's okay. Like in the case that H is the zero polynomial, the quotient polynomial would also just be zero, and like everything is actually really nice for the prover, but it's like still sound. Everything's still sound. Maybe I'm making a mistake, but I don't think so. I think it's just like that. I can't completely rule that out, even though but even if I can't, maybe there is a simple way to rule that out. I'm just not seeing it like offhand since I'm 90 minutes into the session. But even if that does happen, I don't think there's like a soundness error issue or anything.
Okay, thank you.
Yeah, thanks for the question.
I have another question on that. It says, where does the fast Fourier transform comments in play? So that's another term.
Great question. Great question. At some point, I should also generally talk about like what fields can different SNARKs work over, and like to the extent that the answer is not all fields, where those restrictions come from, because it's somewhat similar to your question. So FFTs come in from several places. So one is in the commitment scheme, hashing-based commitments. I said those involve like encode like the coefficients of the polynomial, then hash. And for a lot of codes, in particular what's called the Reed-Solomon code, making encoding fast involves FFTs. Okay, but there are other places FFTs can come in too. They can come in from the polynomial IOP. In particular, if you want, at least if you want to explicitly compute a quotient, that involves polynomial division. You know, so like dividing you know, dividing a degree, I don't know, 2n polynomial by a degree n polynomial. And doing that quickly also involves FFTs. So the FFTs can come in both from the polynomial IOP or from the polynomial commitment scheme, or both. Places it can come in. I think those are the main ones anyway. Maybe I will then talk about like what fields can we work over. And again, so like limitations over, you know, like the field you know, your SNARK can work over come in from several places. It can either come in from the polynomial IOP or from the polynomial commitment scheme. So the limitations come in. So let me start with it. So if you have to do FFTs, so that limits the field somewhat. Okay, and this is why you see people working over baby bear, Goldilocks. Okay, these are fields that support like FFTs. Okay, there's been some work like zk-FFT, you know, kind of gives FFT-like procedures. So I'll just say it gives FFTs over any field that's sufficiently big, but you know, let me vaguely say it has significant overheads. I'll be vague as to what the overheads are, and how much they matter might depend a little bit on context and stuff. So it largely hasn't caught on, but now there's something called zk-SNARKs, which sort of, you know, does, I would say it does better than zk-FFT for a specific field called M31, which is the field of size 2 to the 31 minus 1, which is a really nice field because this is called a Mersenne prime, and this means that field arithmetic is like really, really fast. So it's like 40% faster than the baby bear field, for example, even though they're both 31-bit fields. And so, you know, this is not an FFT-friendly field, but zk-SNARKs has kind of found a way to, but like zk-SNARKs make it not matter. That's sort of what, you know, so like you can kind of do an FFT without doing an FFT or something like that. And unlike zk-FFT, which, you know, is very, very general, but I think has significant overheads in general over this field, zk-SNARKs like really is just as fast as if you were doing FFTs. Yeah, so anyway, so FFTs, if you have to do them, they do somewhat limit the field you can work over, because not all fields support efficient FFTs, but like, you know, caveat, if you're like really clever, you can potentially address the issues. That's sort of the point of zk-SNARKs. If you use a curve-based commitment, okay, then curves can only work over big fields. So you need a 256-bit or bigger, typically prime order field. Now it's not, you know, so caveat, like people have looked at like, so potentially you can use curves to, you know, define like secure elliptic curves, like over like say a degree 5 extension of Goldilocks. So Goldilocks is like a 64-bit field that is FFT friendly that people like. So you do, you know, the field, you can get over 256 bits without having so Goldilocks has characteristic, or it's like a 64-bit field. So you can get to 256 bits without going to a 256-bit prime potentially. You can like take an extension field of a 64-bit field or something. Like extension fields, like curves over extension fields freak some people out. So basically the way to put this is, several years ago, I don't know, maybe 2010-ish or something, people developed much better attacks, meaning much better algorithms for computing discrete logarithms over fields, over extension fields. And so that sort of like permanently turned some people off from designing elliptic curves over extension fields. So, you know, there have been papers that look at like designing a degree 5, like an elliptic curve over a degree 5 extension of Goldilocks, so that like known attacks against this curve, you know, take time, I don't know, like 2 to the 100 or more. I don't know exactly how many bits of security it has. But there are some people who are just worried that there are yet more attacks waiting to be discovered against elliptic curves over these extension fields. So there are people who just think like we shouldn't be doing stuff like this, and we should be designing our curves over 256-bit prime order fields or even bigger primes. So anyway, so you know, up to these caveats, like if you use an elliptic curve based commitment scheme, you're forcing yourself to use like a really big field. This means what this means, by the way, is that like the field has size like 2 to the 256 roughly or more. So like even writing down a field element, you have to write down 256 zeros and ones just to say what field element you're talking about. Whereas in like a 31-bit field, saying what field element you're talking about requires just 31 zeros and ones, not 256 zeros and ones. And then finally, the PIOP might require like somewhat large characteristic, meaning, let me just say somewhat large fields. And so in particular, the constant round polynomial IOPs people use today, so they'll want to index gates in a circuit. I'm putting gates in quotes because, you know, SNARKs like don't necessarily have to use a circuit representation of the computation. They can use something more general, but anyway, they'll index them by like g to the 0, g to the 1, g to the 2, up to g to the circuit size. And this only makes sense or only works if the field has size at least circuit size. So like if the field characteristic, but yeah, if you don't know what a field characteristic is, like don't worry about it. It's not really important today, is at least circuit size. And in particular, so by, you know, by this I mean this notation, I mean circuit size, how many gates are in your circuit or whatever. And the reason I flag this is because this, you know, Binius and related works that are coming out like right now are moving towards fields of characteristic 2. Now they can't use these constant round PIOPs anyway, even if they wanted to, which again, like the point of Binius is a fast prover, and I think these are not so good for the prover, these constant round polynomial IOPs. But you know, Binius is a commitment scheme for multilinear polynomials, and these constant round polynomial IOPs use univariate ones. So anyway, but I do want to flag, like, you know, if fields of characteristic 2 became popular, there are lots of reasons you wouldn't want to use these constant round polynomial IOPs when working over the field. But like one is you literally just cannot work over fields of characteristic 2, since these constant round polynomial IOPs need the characteristic to be at least circuit size, and in practice this typically means at least like 2 to the 20 or something, which is one reason why, you know, you see projects trying to use Baby Bear and M31 these are 31-bit fields. And it's like the reason they don't go much below 31 is because, you know, you can't go below 2 to the 20 for this reason right here. Okay, so let me just think. These are probably the main reasons some SNARKs can't just like work over whatever field you give them. Yeah, I think these are the three main things to be aware of. Okay, so please,
I had a
question.
question about the group commitment scheme that was talked about prior.
Yeah, the multi-exponentiations.
Yes, so those are basically dependent on the KA assumption, right? Knowledge of
Not
exponent.
necessarily. Like bulletproofs, you know, Hyrax. These are all just discrete log plus fiat Shamir.
I see.
Yeah.
So the question I was trying to get to is, this has bugged me for some time, is the KA assumption somewhere reduces to non-falsifiable assumption, right?
Yeah, yes. And I'll just say there's like evidence that that's intrinsic, that like any SNARK needs a non-falsifiable assumption. I mean, at a minimum, I think it's going to be, you know, need some kind of crazy breakthrough in cryptography to, like, there are barriers known, you know, like all known techniques basically aren't going to be able to base the security of SNARK on a falsifiable assumption. But like, you know, for bulletproofs and Hyrax-based SNARKs, fiat Shamir is the non-falsifiable thing. So you don't have to necessarily, like, you have options for non-falsifiable assumptions other than knowledge of exponent stuff.
So my question was that, could you intuitively just give some idea about why the community of this particular community could not have done without the non-falsifiable assumption reliance?
This is, I mean, you know, so the barrier is a result of Gentry and Wicks, which
Yeah.
just says like so it literally, so no black box, security reduction, you know, can base the security of SNARKs on falsifiable assumptions. You know, but there's some caveats that I'm not, you know, particularly conversant in. You know, this is like for quote hard enough, you know, problems. But yeah, basically, like we need to go beyond black box, you know, security, you know, analysis techniques in order to base the security of SNARKs on falsifiable assumptions. And you know, most of our techniques are black box today. I'm not the best expert to, you know, go into much more detail than that on these barriers. But
The question then is that what exactly is in the current SNARK approach that what exactly is the reason in the current SNARK approach that it has to rely on this? Could you say a little
yeah,
bit about
so you can get an interactive argument that's based on standard assumptions, like completely standard things, like just discrete log. Okay, but if you want a non-interactive, you have to fiat Shamir it, and that we only know is secure, at least in this context, in the random oracle model. So we know fiat Shamir is like secure in the plain model in some contexts, but not for succinct interactive arguments. Okay, so that's one obvious place that non-falsifiability is coming in, like today, is like anything that uses fiat Shamir to make it non-interactive, we're going to have you know, an issue with for in terms of non-falsifiable assumptions. And then if you look at something like Growth 16, it's sort of avoiding fiat Shamir, but like the way it avoids it, like intrinsically uses knowledge of exponents or some kind of algebraic or generic root model or something. It's hard for me to say much more than that, but it's kind of getting rid of fiat Shamir in a way that's inherently using another form of non-falsifiable assumptions.
Right. So is it safe to conclude that the fiat Shamir and KA, both of these to reduce to non-falsifiable assumption?
Yeah, or they are non-falsifiable assumptions, I would say. Like they,
Right.
yeah.
Okay.
Yeah.
But I still, intuitively, what I really have been bothered about is that what exactly is the reason that you Like information theoretically, what was the reason you could not prove this without having to depend on that
Yeah,
assumption?
I don't have much intuition for this right now. I can try to develop some.
Yeah.
Yeah, I mean,
Okay.
you know, if you look at what the knowledge extractors tend to do, like you know, the nicest knowledge extractors anyway, you know, like for Fiat-Shamir based SNARKs, they watch the random oracle queries that the prover makes while it's constructing the SNARK proof, right? And that's like their reasoning about like what was happening in the prover's head that's not visible to any external party like in the real world. And similarly, knowledge of exponents, like assumptions, are just assume that the only way the prover can like, you know, compute certain information is to go through a certain specific computation. So like these, you know, intuitively non-falsifiability is like kind of making assumptions about what happened in the prover's head as it computed a proof. And like you know, certainly our nicest witness extraction procedures, you know, to like pull a witness out of the prover, that's what they do, is they like look at how the prover computed the proof and they identify the witness in that procedure. And like that's clearly non-falsifiable, like what's going on there. I guess I'll try to say something more at some other time. I actually, yeah, this is more in the weeds of like the security reductions than I tend to go myself.
Oh, thank you, sir.
Great. Oh, wow, I am at 2 hours in. Huh, okay. Well, again, I don't want to talk about this next week, so I am going to just keep punching ahead, and don't feel bad again if you sign off. If this doesn't get recorded, I will just repeat this at some other session and make sure it gets recorded, because I think this information is important. I also plan to put it in a blog post at some future points, hopefully not too distant in the future. So yeah, so I want to talk about field ops, MSMs, and generally group operations, pairings, and hashing. Okay, so let's start with field ops. Okay, so talking about how expensive is a field op. Annoyingly complicated because people use different fields of different sizes in particular. So let's just start with like 256-bit fields. Okay. And again, these fields are the ones that any curve-based scheme is going to want to work over. Okay. So here, if you're, typically when you work over these fields, unless it's like a very, very, very special 256-bit field, if you want to multiply two field elements, you'd use an algorithm called Montgomery multiplication. Okay, and this means, I'm not going to go into detail here, but like rather than storing like the field elements themselves, like you actually store, to store the field element A, you actually wouldn't store A. You'd store A times something else R. So some other field element. And this just, it's sort of meant to, okay, so I haven't talked about modular multiplication yet, but that's these prime order fields. That's what multiplication involves. So it's like field elements are just numbers between 0 and some prime. But when if you take two numbers that are both between 0 and that prime and you multiply them together, then the number might be much bigger. It can go up to like the prime squared. Okay, and so with modular multiplication, you just sort of do a wraparound thing. So like, your numbers are getting bigger and bigger and bigger and bigger as I draw this line. But once they go bigger than the prime, the circle. So yeah, so here we have like 0 in the field is the same as the prime, is the same as twice the prime, is the same as 3 times the prime, or in general k times the prime for any k. So as the numbers get bigger and bigger and bigger and bigger, you wrap around and start at the beginning again. That's how multiplication works in prime order fields. Where in 256-bit fields, that means the prime is about of size 2 to the 256. So, there's about 2 to the 256 field elements. All right. And so, the Montgomery multiplication, basically, it doesn't store the field elements themselves. So like the field element 1052 would not be stored as, you know, the integer 1052. Rather, you'd multiply the field element by some r, and this r is chosen basically so that it makes like wraparound faster to compute, to deal with, right? Because like the naive way to do wraparound, like if I want to know, you know, some, you know, I take two field elements A and B and I multiply them together, and you know that's up to, you know, is as big as 2 to the 512. You know, so I want to compute the wraparound, you know, so A times B mod P. Like the naive way to do it would just be to divide, you know, write, this is naive. You'd write A times B, which is 512 bits. You'd write it as, you know, like Q times P plus R. And this R would be, you know, like, this is the wraparound. Like this is the value you actually want, like the right value. Okay, but this computing Q and R requires division by P, and like division is slow. You don't want to do division. So Montgomery multiplication, you know, does the wraparound without division, and for, you know, to make that nice and fast, it doesn't store A itself. It stores A times some other field elements, and that's all I'll say about it. But basically, for 256-bit fields, like a standard CPUs can do a multiplication in about 40 CPU cycles. Okay, roughly. Additions are only about, so additions I think are only like 6 cycles. And so what this means is in big fields, like 256-bit fields, like adds are much cheaper than mults. Additions are much cheaper than multiplications. Again, you should think of these fields as like the numbers that arise in the prover's computation. And so, you know, 256-bit fields, the numbers are really big, but like a 31-bit field, the numbers never get bigger than 2 to the 31. And so in big fields, additions are pretty cheap, and often people will just treat them as free. Now they're really not free. Like, you know, I think, you know, six cycles for an addition is still only, you know, about 7 times cheaper than 40 cycles. So, you know, if you do 7 times as many additions as multiplications, like you really can't ignore the cost of the additions. But anyway, you know, up to, you know, first approximation, like the additions aren't a big deal, but the multiplications, they cost like 40 cycles. In, you know, like 31-bit or 64-bit fields, the multiplications would typically, I think, not be done with Montgomery multiplication, certainly not in 31-bit fields. And they can be as low as, you know, like 6 cycles or something. I don't know the exact count. I haven't looked at it recently. And additions, you know, can be as little as like 1 to 3 cycles, I guess. Okay. So it gets, you know, it gets pretty annoying to compare. What I just said is like a very clean comparison. You know, it's like this is how much multiplications in big fields cost. This is how much multiplications in small fields cost. But then you run into, on CPUs anyway, you run into something called vectorization, which is a complicating factor. And what happens is these there are certain like sometimes you need fancy hardware to do this, things like AVX2 or AVX512 from Intel, and I think Apple has, I think Neon is vectorized, has Neon is vectorized instructions. And so AVX512, that refers to, there are some 512-bit registers. Okay, and so with these, like you can write down, like I think 512 over 31 is, what is that, like 16 or something? And so you can write down 16 31-bit field elements into one register here. One register is like one memory cell or something. Okay, and so you can potentially do, you know, like 8, you know, like field additions or multiplications, you know, like in parallel in one CPU cycle on these machines. You know, if you're dealing with small field operations. Okay, on the flip side, so there's this view that big field operations are not really friendly to vectorization. And certainly, if you conceptualize big field elements as 256-bit bits, well, you can 256 bits, well, you can only stick, like at most 2 field elements in a 512-bit register like AVX512 has. But I actually think that is probably going to turn out to be a misconception. And I expect vectorization to also benefit operations over big fields. So we'll see if this prediction comes true. But Montgomery multiplication does wind up breaking 256-bit field elements into several 64-bit words. And you can pack many of those words into one 512-bit register. And thereby, potentially get the number of cycles required to do a 256-bit multiplication, at least if you're doing many of them, down significantly below 40, I think. So anyway, this is today it's a nuisance that vectorization is sort of known to benefit small field operations, and not known to benefit big field operations. But I expect we'll see that it also benefits big field operations. And if it benefits them just as much as the small field ones, then the comparison between a big field operation and a small field operation will become pretty clear again, at least on CPUs. Okay, so just so that's field ops. All right, and I could say a lot more about this, but that's probably enough detail. And the only reason I had to talk as long as I did about field ops is because people try to work over many different size fields. But there are other factors that affect how fast these field ops are. Like I told you, like M31 is like a really nice field, and basically because the prime is so close to a power of 2, you can do reductions modulo that you can do the wraparound like really nicely, whereas Baby Bear is not so close to a power of 2, so the computing dealing with wraparounds is not quite as nice in Baby Bear, and it potentially makes like a 40% difference. I do need a flag here that CPU cycle counts, I actually think they're a pretty good way to understand the costs of SNARKs. They're certainly a more detailed way to understand what things actually cost than a lot of what people do today, which is essentially just guess. But they're not the end of the story, both because ultimately, the provers and verifiers might not necessarily run on CPUs. They might run on ASICs or FPGAs or GPUs. But also because some operations may be memory bound, meaning cycle counts aren't really the right cost measure if like cycle counts will treat a read to memory as like the same cost as anything else that takes one cycle, like adding 2 numbers or something. But like some operations are what kind of the bottleneck is just waiting around for the memory reads to come back because you're doing so many reads to memory or something. And in that situation, like modeling a read to memory as the same cost as adding 2 numbers that are already in registers is not the right thing to do. So I'm giving you cycle counts, approximate cycle counts for field ops in various fields. I think that's important and useful data to have. It's not the end of the story, certainly. But I've managed to achieve like very accurate predictions as to like Jolt's performance over the last year by developing like very detailed cycle counts of what the prover is actually doing. So it seems that memory bottlenecks are not a major issue, at least in something like Jolt. It could well be an issue in other SNARKs, though. Or if, as we change the commitment scheme in Jolt, it potentially something becomes memory bound, whereas today nothing is. Okay, so that's field operations. Now, one of the nice things about group operations is group ops can be expressed directly in terms of field ops because the groups themselves are defined over the field. Okay. So what, a group op, what I mean by that is like in a multiplicative group, by a group op, a lot of people will call it a group addition, but like I like multiplicative groups, so I would call it a group multiplication or a group operation. Means a group op means taking two group elements A and B and computing the group product A times B. So people will call, again, I'm calling it multiplication, but a lot of people will call this group addition. Okay. Now, a group, a group op, a group addition, if you will, again, I'm calling multiplication, at least on CPUs, tends to be 6 to 12 field multiplications. Okay, so like you can directly compare like the cost of the prover doing one group op to the cost of the prover doing one field multiplication. It's, about an order of magnitude more expensive. Okay, now let's talk about MSMs. Right, remember an MSM of size n computes like, so, GI to the CI. So each of these will be called a group exponentiation, or people will call them scalar multiplications if they're using additive group notation. And then this would be, the group, group multiplications, or people will call them group additions and additive group notation. So I'll just call them group ops. So naively, this would be, n group exponentiations and n group operations. Okay, and now a group exponentiation would be up to several hundred, say up to 400 group operations, right? This is because these exponents can be as big as the group size, like the field size. So they can be as big as like 2 to the 256. Okay, and so like computing G to the 2 to the 256, basically the fastest way to do that is something like you compute G squared, and then you square that to get G to the 4th, and then you square that to get G to the 8th, then you square that to get, so you just get powers of 2, maybe it wasn't 8th, maybe it's 16th, I can't, anyway, so you have to do this 256 squarings before you've computed G to the 2 to the 256. And again, the exponents in these groups can be as big as 2 to the 256. And the reason I wrote 400 and not 256 here is because if the exponent is not a power of 2, you pick up even more group operations, because you can't just do squarings, you have to do some other stuff too. So that, if you're naively computing an MSM, these n exponentiations are by far the bottleneck. So that's like 400 n group operations, which, remember is, roughly, it's like 2400 n to, like 5000 n field ops. So if you naively implement an MSM, right, it's like really expensive, right? It's like if there are n terms in the MSM, it's like you're doing 5,000 field ops per term in the MSM. Okay, that's like, that's 5,000 times. That's really bad. Like yeah, you don't want to do 5,000 field ops for like every gate in your circuit or something like that. That's you want to avoid that if you possibly can. Okay, so however, so that's if you do MSMs naively, okay? But there's something called Pippinger's algorithm, which unfortunately seems to not be as widely known about as it should be. It's not that it's some like esoteric thing, but like I do regularly encounter, people, working on SNARKs that haven't encountered this algorithm before. Okay, and that improves over the naive MSM procedure, okay, by a factor of about log n. All right, and I think you can roughly think of this in most SNARKs as, you know, something like about 20. Right, so if you're committing to like 1 million field elements because your circuit has 1 million gates in it, log n would be 20. So actually, it could really be as big as like, you know, 30 plus, you know, because you can easily have gates with billions of values in it, and then it's like 30 plus. Okay, so I mean, this 30x factor is like really significant, right? So now you'll go from, you know, an MSM of size n, you know, rather than it taking like 400 group ops, like 400 n group ops, it's only going to take 20 n. Okay, and now this is not so bad. So I mean, you know, that's still like 120 to, you know, 250 field ops per like committed value. But you know, 250 or something is much better than 5,000. Okay, and by the way, like yeah, so you know, these MSMs typically come in because the prover's committing to values, and like, you know, the MSM has n terms in it, you know, when you're committing to n values. So, you know, I like to think of these costs here, like 20 n group ops means 20 group ops per committed value. So committing to n values, it's, you know, 20 group ops for each of them. And, you know, 20 group ops for each of them is like 250, you know, 256-bit mod malts or something like that. Okay. So that's how to think about MSMs. You can just directly relate them to field ops, and I already told you what field ops cost in terms of like CPU cycles. Okay, now a key point is with recent advances, so recent polynomial IOPs allow the prover only to commit to small values. Okay, and so this means that while, you know, field elements have 256 bits in them, like to write down a field element, it takes 256 zeros and ones. That in fact, all of the field elements that these new provers ever commit to, well, a lot of them might just be in 0, 1. And even the bigger ones might be in like 0, 1 up to, I don't know, 2 to the 20 or something. So like 20, you know, all, you know, so while the field SI is 256 bits, all of the committed values each only consist of like at most 20 bits. Okay, and these can be committed much faster than just what I wrote above, 20 group ops per committed value, right? So you can actually get this down to something like 1 group op per committed value. Okay, and the reason is basically because, you know, if I want to compute, like, let's say you just have a 1-bit value. So you know, if I want to compute g to the x, where x is in 0, 1, right? Well, you know, like that's either g or 1. So either way, I don't actually have to do any group ops to get g to the x. And in general, you know, if I want to compute, you know, g squared, that's, you know, only 1 group op. So, you know, before I said the reason like naive multi-exponentiation computation was so slow is because raising g to like a giant exponent like 2 to the 256 is really slow. You need like 256 group ops to do that. Okay, but if, you know, if all of the exponents are like that ever arise are at most 2 to the 20, you would, you know, you only ever need 20 group ops rather than 256. So what's, you know, small exponents means the exponentiations are just much faster to compute. So the way I think about it is, you know, if you were really naive about your MSM and it was like a completely general MSM, you need something awful like 400 group operations, per committed value. But if you're not quite so naive and you use Pippinger's algorithm, it falls by a factor of 20, and 400 falls to 20 group ops per committed value. But then if your PIOP is really nice and all of the committed values are small, you save another factor of 20, and this 20 goes all the way down to 1. Okay, so that's MSMs. So what that basically means is, at very high level, committing to one small value with an MSM-based commitment scheme, whether it's KZG or bulletproofs or whatever, is the same cost as just like 6 to 12 field operations. Okay, which is like pretty good, right? Because the way you should think about things is like, if I have a circuit with n gates, depending on what polynomial IOP I use, maybe I only have the prover commit to n values. Okay, which and I'm saying committing to them maybe only takes like 6 n field ops. But even evaluating the circuit, like with no proof at all, so just like native evaluation of the circuit gate by gate, evaluating the circuit like still takes n field ops. So the time it took me to commit to the circuit was only 6 times slower than the time it took me to just evaluate the circuit. Like that's pretty good. Like most SNARKs today, like the prover actually takes like 1 million times more than just like running the computer program or evaluating the circuit or whatever. So factor 6 is like not really, is pretty good. It's not a big deal. Okay, so I think that's how you should generally think about group operations and MSMs. You should just relate them to field operations. And again, field ops, we talked about sort of what they cost on CPUs. Let me pause. The last thing I'm going to talk about, I think, is, I forgot pairings, and that's just like one sentence. So I'll cover that after I pause, and then I'll get to hashing, and then we'll wrap up. Sorry for blasting through so much time today. Does anyone want to ask any questions? No? Am I still on the call? Can someone unmute and confirm I haven't dropped off the call?
All good?
Yeah, all good, all good.
Yeah.
Okay, great. Okay, actually, I want to say pairings and I want to say FFTs, and then I'll do hashing. Okay, so pairings, again, most of the time, this is like a dominant cost for the verifier. If you're using like KZG commitments or gross 16, it's not really a major thing for the prover. But one pairing, that is one bilinear map evaluation. If you don't know what this is, I described it briefly last time, don't worry about it. It's something like about 1,000 group operations, last I checked. Okay, so these are beefy, right? These are not super cheap. So yeah, I mean, you'll see like I think in something like zero morph, I think the verifier does like log n, where n is like this number of committed field elements, like log n group ops, and then 3 pairings, and like for sure the 3 pairings are the bottleneck for the verifier, right? At least in terms of like total time. I'm not talking gas costs here. Like I don't actually know offhand what a group op. I think a pairing is like 40,000 gas, but I don't know what a group op is. But like in terms of just like actual runtime on a CPU, like the 3 pairings correspond to many thousands of group operations, whereas log n group ops is only ever going to be like several dozen group ops. Okay, now let's talk about FFTs. So if I do an FFT of length n, if I'm able to use like the standard Cooley-Tukey FFT algorithm, which you can use in like the baby bear field or the Goldilocks field or whatever, I think that would be like n/2 field multiplications and 2n field additions. Okay, but then if n is big, so greater than like 2 to the 14 or something, this can start to be memory bound. And so, you know, the right way to, so like looking at cycle counts for the field ops might not be capturing the true cost of the FFT. So, you know, especially in like parallel, when parallelized, you know, on CPUs or something like that. But yeah, so sorry, I messed this up. It's got to be n log n. It's got to be something like this. So log base 2 of n. So yeah, so like if let's say n is 2 to the 20 again, like, you know, then the number of multiplications would be like, so this is like 10n, and the number of additions would be like 40n. Now, oh, I forgot to mention, I guess, like, or maybe I did say it. You know, people are typically trying to do these FFTs in pretty small fields, like Goldilocks or Baby Bear, because, you know, because they often come up. Well, you know, the one big reason they come up is if you're using like one of these hashing-based commitment schemes that has a, you know, Reed-Solomon code used inside of them. And, you know, one of the big reasons people want to use hashing-based commitment schemes and not a curve-based commitment scheme is because it lets you work over one of these small fields. Although I think the benefits of that have been overstated, there are definite benefits to that. And so, yeah, so many times, like the FFTs people are doing in SNARKs today are over these small fields. And over these small fields, adds can be almost as expensive as multiplications over small fields. So that's, you know, I've seen some of these cycle count estimates that, you know, you can debate whether anyone really should be using cycle count estimates for the limitations I described above. I actually think they're pretty useful. But if you are looking at small fields, you should make sure, like, you know, not to ignore the adds, because, you know, they can be, you know, pretty close to just as expensive as the multiplications. Yeah, so I guess something to highlight here is, like, on the one hand, like, you know, this 50 factor in front of the n is like actually much higher than the factor 6 we saw in the MSMs when you're committing only to small values. On the other hand, the field is much smaller. So like one field op, you know, this is like 50n field ops versus 6n field ops. But this is 50n field ops in a small field, and this is 6n field ops in a big field. So, you know, you have to go to like the relative cycle counts to understand, you know, is 50n field ops in a small field better or worse than 6n field ops in a big field? Okay. But one thing I want to point out is, like, the comparison is actually not that clear. Like, you know, I think like the benefits of small fields over big fields in SNARK design have been overstated. And here you're starting to see that, where, you know, the MSM based commitment can do a commitment in 6n field ops over a big field. Is that really, you know, worse than 50n over a small field when you also are more likely to be memory bound? You know, that's not a clear comparison, even though people would have you think of it. It is a clear comparison. So, okay, so that's FFTs. And then finally, there's hashing. All right, so I had some notes on this. So hashing is like the one, but I don't have the notes in front of me, unfortunately. So I might have to just briefly return to hashing next time, which is, since we're at 2.5 hours, I think no one's going to complain. What I will say now is hashing is the one thing that, you know, cannot in general just be directly related to field ops, unless you're using a SNARK friendly hash like Poseidon or something, which again, I actually don't think are particularly SNARK friendly, is what we're going to discover in the long run. But today, these are still considered SNARK friendly. So not surprisingly, you know, because SNARKs work over finite fields, these SNARK friendly hashes like Poseidon are defined over finite fields. And so finite fields. So with them, you actually can, you know, like look at So with something like Poseidon, you can look at the number of field addition and multiplications the prover does, or sorry, the required in a hash evaluation. So the hash function requires. So I think I want to, that's not an exercise I've really seen people do. And so I definitely don't, I'll look at it, this week and see if I want to try to engage in that exercise live for the whole world to see. Might be a bad idea. But in principle, like if you're using Poseidon, you can actually express the evaluation time in terms of field ops and then directly relate those field ops to these field op counts I had up here. Again, with the nuisance that people like to use Poseidon over Baby Bear or Goldilocks, but the MSM based things work over 256-bit field. So you have to do some conversion, of relative cost of the field ops in these different fields, and vectorization is a controversial confounding factor there, and blah, 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 blah. But, something like SHA or Ketchak, which is a standard hash function, just has nothing to do with field ops. And so you can nonetheless relate them to field ops with micro benchmarks. Right. So you just hash a bunch of stuff and, do a bunch of group ops and just see how long they take. And, on some CPU, and that will give you some very rough sense of, what the cost of hashing is on that CPU compared to the cost of field ops. And since I don't have my notes in front of me, I don't want to do make any assertions today. I was planning on making some assertions, but I won't. I'll come back to this in the near future. So I'll tell you in the near future what they'll say. So it's a little existing, like if you go to certain tools like zk-Calc or something, they'll always be missing something. I think it doesn't have hashing in there, right? So exactly what the micro benchmark I want, to relate everything to field ops, people just don't seem to have really published before. But anyway, so my vision, for how we should think about SNARK performance is everything should be related to field ops. You do have the nuisance that different SNARKs work over different fields. That will always be a nuisance. But I think you can, it's an addressable nuisance. And then if we're using standard hash functions instead of algebraic ones, I think you just do some micro benchmarks and get a rough sense of the cost of hashing and the micro benchmarks relative to the field ops. And at that point, we've related everything to field ops. And so when I try to ascertain how expensive is one SNARK or another SNARK, I try to just put everything in terms of field ops. And while in practice, there are all sorts of confounding factors that we've discussed today, I actually find that in the, if you have enough engineering thrown at the SNARKs, that actually reflects pretty well on the relative performance that comes out, after enough optimizations has been done, that, things are no longer severely memory bound and stuff like that. So that's why my presentation today expressed all costs in terms of field ops, and I hope that catches on. And I'll try to, talk more about this in future, posts and sessions and things like that. Yeah, okay, so that's everything. Thanks for staying till the end. Again, I promise there will not be any 2.5-hour sessions as we go through the book now. The content will be selected to not take this long. I did a bad job the last 2 sessions, just estimating things. So if anyone wants to ask, I'll stick around for another few minutes, no more than that because it's so late. But I appreciate your time and hope this was useful. And now, as we see how the SNARKs are designed, you have a reference point for, well, this one does MSMs, what does that cost versus that one that does hashing and FFTs, what do those cost? And you can actually, again, it's very crude. I'm not claiming this is a very precise way to compare a curve-based commitment scheme to a hashing-based commitment scheme. But I think you can get a decently accurate sense within a factor of 4 anyway, something like that, of how the two will compare on CPUs anyway. And that's much more accurate than seems to be, you know, the case with the general discourse today. So I think this I wanted to have this information like at least available as a reference to people as we dive into what's happening in these SNARKs. So I'll stop rambling here, and thanks again. Hope to see you next week.